second lecture in Introduction to Robotics. In the last module, we covered what a robot actually is, and we came up with the definition that a robot is a physically embodied, artificially intelligent agent that is capable of sensing, planning, and affecting the physical world. So you see, we are pushing the definition a little bit from not just doing computing, but to do something a little smarter than this, and you really using AI techniques that we learn in computer science versus just connecting sensing and actuation in the most simple way. We also looked at the concept of mechanism intelligence. We had this little demonstration of a robot that doesn't fall off the table just using the mechanism alone. And I think it's important to understand that some very hard problems become very easy with the correct placement of sensors, actuators, and structure. For example, if you have a robotic hand that has a camera right in the palm, it can see these blocks all the time, which is a much easier problem to solve in terms of the algorithms that you have to come up with and the code that you have to write, than if the robot arm can potentially occlude the blocks when the camera is mounted somewhere else in the environment. So it's difficult to really teach this. You can look at bioinspiration for that. But in general, the message for this class is this is an art that I want you to keep your eyes open for and to understand how dramatically it can affect your solution quality. And at the end of the day, robots are not just computers, but are in the physical environment. We've been also talking about collaborative robots. These are robots that work very closely together with humans, and they are adding to industrial robots a sense of sensing forces and touch, as well as to a limited extent visual sensing to understand what goes around them. We have safety systems in these collaborative robots that will cut off the power when the robot exerts too much force in an unexpected way and understands what the humans do around it. The really big advantage of collaborative robots in practice is that they are much easier to program for humans as they are safe, so the human can be together with the robot, move it around, see immediately what it does wrong, understand what needs to be done and fix that. Therefore, work much closer in a closed loop with the robot during programming. Conversely, robots are often then replaced with cheaper and simpler industrial robots that can move faster once they have been demonstrated in a certain environment. One note on the administration of this class: you might have seen that there are many ungraded practice quizzes, including in the videos that we have available on Coursera. You do not need to do those in order to pass the class, but I want to let you know that most of those questions are repeated in the final exam for each part. That is, if you want to do well on the final exam right away, please go and do all these ungraded quizzes as well and really try to understand what we are trying to teach here. All right, so today's focus is on basic sensors and actuators. And first, let's look at a sample of everyday sensors. For example, the most sensors nowadays you will find in your smartphone, and we have a little timeline here for the Samsung Galaxy, what kind of sensors it has. And as you can see, in just 5 years, the number of sensors triples. We can now measure heart rate. We have proximity sensors built in. We have even 3D sensors in later generations that are like the Xbox Kinect that has been developed for gaming, but are now so small that they can be integrated in a smartphone. We also have the car industry as a reliable source for sensors that are used in robotics, starting with the ultrasound sensors that you might be familiar in the back of your bumper that allow you to not run into small obstacles like this one here, as the car will start beeping or even showing you a graphical representation of the obstacles that are behind. Cameras are now ultra cheap, also driven by the cell phone, and often they are now integrated in the rear view mirrors and other places in the car. So you can often see backwards, you can see what is around the car. We do have radar, which is now becoming dominant in most new cars, and it helps you with keeping your distance to the driver in front of you. But the real key point I want to make with this slide is that there are actually almost no sensors that have been developed for robotics. Robotics are usually just the benefactor, as the larger industries in consumer electronics are developing or adapting a certain type of sensors. They become really cheap and available. And probably the most impressive example here is the Xbox Kinect that has been developed for gaming and now is able to deliver 3D information at a fraction of previously available technology. And the emergence of low-cost drones, which are heavily relying on gyroscopes and accelerometers and magnetometers, which are being part of smartphones since very early on. All right, let's try to understand some of these sensors. And here my goal is to really give you the principle of operation so you understand how these sensors operate in principle and what they measure, which will dramatically help you when you use them in your robot. We are not teaching you how to build these sensors in practice. This is usually an electrical engineering or mechanical engineering class at advanced level. For example, an accelerometer now can be created with so-called MEMS, which is micro electromechanical systems technology, and allows you to build something like this springboard here at a micrometer scale. And the springboard is a good example on how the accelerometer works. The idea is that the springboard is like a spring that has a spring constant and has a mass on top of it. And we know from Hooke's law that the force that you need to bend that springboard is the spring constant K times the displacement X with which you displace the springboard. We also know from Newton's first law that the force that you need to move something is the mass times the acceleration. Now, when you consider this scenario here, we do have acceleration that is working on the mass at the tip, which is gravity. It's 9.1 meters per second square. And so we have now gravity exerting a force onto the tip here as a function of the weight that we put here. And that force is F equals m times a, which is the same as the spring constant times the displacement. And therefore, by measuring the displacement and knowing the spring constant, we can work out the acceleration that we are seeing here. Now in MEMS, this works the exact same way. We have a bending spring here. We have a little mass at the top. When you move this thing to the left or right with a certain acceleration, inertia will make the mass at the tip stay, and we can measure the displacement using capacitive sensing here, and we can infer acceleration. In practice, we are usually using three of these things orthogonally to each other. That is, we can measure acceleration in 3 axes, top down, left, right, and back and forth. Another class of sensors that are very prominent in smartphones are rate gyroscopes. And I said the word rate gyroscopes because they measure speed, while gyroscopes themselves measure pose. And it might be easier to first understand the gyroscope. You all know this mechanism here. When you spin a top up like that, you can move the outer rings independently of the inside, while the inside keeps spinning and keeps itself in place using rotational inertia. Now, if I put this thing on the cannon of a tank, for example, and I drive around, this will stay still with respect to its initial launch pose, and the outer rings will move. If I can measure that angle, I can measure the orientation of the tank cannon, and this is actually how it was done on tanks 30 years ago, selling a device like this for 100,000 euros and really mechanically measuring the pose. Now, building this, making this smaller is still difficult, but what people do instead is they create rate gyroscope where you only measure the rotational velocity. A simple mechanism to do that is using a light source that has been run into a light guide and then detected on the other side. And what you can do is you can look at the phase of the light that you send in and the phase that comes out. And now when you start spinning this coil to the left or to the right, the speed, the relative speed is affected, and there will be a phase shift that I can measure. And based on the phase shift, I get the rotational velocity of this. I can also create a simple mechanical system like a spinning, like a vinyl disc player, where there is a mass on top, and I can build this in MEMS, and instead of spinning it, I vibrate it in a rotational way, and I can then measure the way the masses move to infer the Coriolis force, and from that I can get the rotational velocity. Applications for this is correct heading in a robot. I might place an accelerometer on the robot, which I can use to integrate the position. With the gyroscope, I can start integrating the pose, and these are concepts that we talk more about later in class. But these two, accelerometer and gyroscope, are really part of most robotic systems that have a so-called inertial measurement unit, also known as IMU. All right, next class of sensor that is very important in mobile robots and arms alike is the wheel joint encoder. It is used to tell the orientation of a wheel or a robotic arm. The way this is done, I have a robot joint which has a motor, and together with the motor I put a disc that literally has a pattern like this, black and white alternatingly. Then I have a little sensor that can measure as black and white passes along the sensor, and from that I can count the number of ticks that the motor has been turning. Now, if I also want to know not only the number of ticks but the direction, I can use two discs that are slightly interleaved, and now I can see a code like this using two sensors. And from that I can tell whether the outer disc comes first or the inner disc comes first, and that tells me the direction. It is also possible to get absolute encoding. In this case, I have placed a binary code. I need 4 sensors, and with those I can read the exact absolute orientation of my encoder on the motor. These also exists in a linear way, where I essentially put barcodes on a linear track, and then I can read at any point in time where the motor is. Now, this introduces an important concept, absolute and relative measurements. The absolute measurement gives me the actual position. The relative measurement gives me only the speed or the relative motion at which something happens. This is the same with the accelerometer that you've just seen. It's a relative measurement. It's the acceleration, which is the derivative of speed, which is the derivative of actual motion. And the gyroscope, or the rate gyroscope, which is the derivative of the speed of the absolute orientation. All right, the next class of measurements that we take very often in robotics is distance. A very, very, very simple way of doing this is to emit some light of known frequency, like infrared, and measuring how much of that light comes back. A sensor like this usually has two parts. One is to emit the light, the other one is to sense. And as light decays quadratically with distance, we will see a very highly nonlinear response. So when I'm very close, I get a lot of light back, and as I go further away, the amount of light that comes back diminishes. So I need to turn it into a linear measurement of distance, like in meters, but I also will probably see a lot of reduction in accuracy as I go down. We can also measure distance from much more sophisticated information, and this is an idea from 2002 that precursors the Xbox Kinect. And the idea was to say, if I project a pattern that I know, like lines, colorful lines that are straight, they will be deformed in some way depending on the stuff that I shine that light on. And if I can infer the math that relates distance or surface distance to the amount of bending that I see, then I can reconstruct 3D information. And so here you see an example where I have hands, I project a light that is really straight lines, and then I infer the 3D pattern. In the Xbox Kinect, we believe this is done using a pattern, a speckle pattern, where I know exactly where each of these points should be if there wouldn't be any obstacle, and from that I can backtrack the actual depth that I must have shined that speckle pattern on. I can also use sound to measure distance. Again, I have a emitter-receiver pair. This is much bigger than the one for light. I emit an ultrasound chirp, it's called, and I listen until it returns. Now, the speed of light is 300,000 kilometers per second. The speed of sound is only 300 meters per second. So the time I have to wait until this comes back is actually non-negligible, and I usually have to wait a few milliseconds for the sound to come back, and only then I can take the next measurement. Important class in robotics is measuring distance from laser. These are devices that have been originally built to protect industrial installations from humans to enter them. They would create what was known as a light curtain by emitting a laser ray, as you can see here, at very high speed. And if a person would walk into this laser, we would be able to detect this, and these devices would physically shut down the power to the plant. When they came out, roboticists very quickly adopted those to allow a robot to localize itself in an environment, map it, and then navigate it. And this got pushed to the top by people putting up to 64 of these rotating mirrors into a single package, putting it on top of a car, and use it to look ahead 50 meters around the car and track everything that is around the car. Now, Tesla is not using these kind of sensors, and there's, if you read the news, sometimes there's some public discourses on whether you should be able to do autonomous driving using cameras alone, like Tesla believes, or whether you have to mount these laser scanners. There are pros and cons. The laser scanners are, of course, expensive. They also don't work very well in rain. Yet we like to have more data than not. But here I want to explain real quick how they actually work. What is done is the laser is at a very high frequency, and what we can do is we can modulate a signal at a much lower frequency, like 5 megahertz, onto the laser. When I say modulate, the laser will actually turn a little bit darker and then turn brighter and darker and brighter at this very high frequency of 5 megahertz. And what I get is a wave that stands in the air, and here the laser is brighter, and then here it is darker, and then it gets very dark and it gets brighter again, and at some point it hits something and it gets reflected. Now, as it gets reflected, I can see that there's a phase shift in that wave, and that is what the laser scanner is actually measuring very quickly. So the laser scanner does not measure the time of flight, which now also exists, but actually measures the phase shift of some modulated signal. In this case, the signal has a frequency of 5 megahertz and a wavelength of 60 meters. And with that, I can measure distances up to 30 meters ahead. All right, so we've seen a couple of examples of important sensors. We will now talk about how to classify them. And I jotted down a couple of things that we can note for each sensor. The first one and most important is probably what is the type of information that I get. And we have seen distance, we have seen acceleration, we have seen velocity. We could then say what the physical principle is that we are using. Is it measuring sound? Is it measuring phase shift? Is it measuring the displacement of a spring inside a MEMS device, and so on? We've also already talked about absolute versus derivative. This is very important. A laser scanner is an absolute measurement of distance. It's not a derivative one. We have something we didn't talk about, which is the amount of information that the sensor provides, or the bandwidth at which frequency it can give you this information. There is a fancy word called dynamic range, which is the ratio between the low and high reading, which is usually expressed in decibel. And very important are the accuracy, precision, and resolution. So when you look at the laser scanner, you usually get like a little data sheet like this, and you can go and look out for these things like range. And in this case, the range is 3.98 meters, which is the difference between the lowest and the highest reading. The dynamic range is the ratio of these two numbers. The resolution is the minimum difference between values. It is provided here. So it comes in increments of 1 millimeter. The linearity is the variation of the output as the function of the input. And in this case, it doesn't really say much about this, but what it does, it shows you that the accuracy, which we talk about in a second, is plus minus 10 millimeters up to 1 meter, but then becomes 1% of detected distance. So what this means is the accuracy can be much lower than 1% as you get closer. So the sensor is somewhat non-linear. The bandwidth is the speed with which measurements are delivered. We have it here, it's called scan time here. It provides measurements at 10 Hertz, or 10 times a second. This thing provides an entire sweep. Cross sensitivity is the sensitivity to environment. It is not given here, but it might explain what laser wavelength we are getting. So we can see that if we send something with 785 nanometers onto that sensor, then the sensor is probably being confused. The accuracy is the difference between the measured and the true value in percent. And in this case, we are given a percentage of 1% up to 4 meters. And finally, we have the precision, which is the reproducibility of the results. And that is information that is not given here. So what does that really mean? Let's go to this slide real quick. We have precision versus accuracy. And when you shoot darts at a crosshair, and you have these black dots where the dart is landing, a pattern like the one to the left is neither precise nor accurate. A pattern to the right is very precise and very accurate. Now, what's the difference? When you look at these two in the middle, I have something that is very precise but not accurate. And I'm saying this because it is precise, it hits very close to the same point, so it's very repeatable. But it's not accurate as it doesn't actually come close to the real value. This measurement here, the third one from the left, is very accurate, but it's not precise at all. Why is it accurate? When you average these measurements, you will see that you can pretty accurately estimate the center, but it's not precise in that it's not very repeatable where they land. So we can now also do this exercise for the ultrasound sensor. And here, this is a very cheap device that you can buy online. And it doesn't come with a data sheet, just with this little snippet that I copied from the website. And we can see if we can actually do that exercise and understand what the different quantities are. So the range is, it goes from 2 centimeters to 4 meters. So the range is 398 centimeters. The dynamic range is the ratio of the lowest and the highest reading. So I have to divide those two numbers and then take the logarithm. That gives me a decibel reading. The resolution is 0.3 centimeters. And now this is interesting, because do you really think it can measure so accurately? No, the accuracy is much lower than this. It only means that it will provide you measurements in increments of 0.3 centimeters. So you won't be able to measure anything below 0.3 centimeters between two measurements. The linearity we don't know anything about. The bandwidth we should find here. And no, bandwidth is not given as well. The cross sensitivity is not provided. The accuracy is not provided, and the precision is not provided. So this is not unusual. What usually happens is you would buy a sensor like this, and then you would do experiments in the domain in which you want to use your sensor. Let's say you want to establish whether you can detect a little tricycle behind a parked car. Well, what you need to do, you do an experiment with devices like this, smaller and bigger, and then you can determine experimentally how small a device can be, or like an obstacle can be, for you to detect. And likewise, you could put like a piece of paper in front of it and estimate the distance or measure the distance with the sensor, and then write down those numbers and create a plot much like this one to experimentally determine your accuracy and precision. All right, for the mathematical definition, I told you already, accuracy is related to the difference between the true value and the actual measurement. In order to get that 2%, we are using this equation here. So if the measurement and the true value are the same, the accuracy is 1, that is 100%. Now, if the true value is not the same as the measurement, I will have the denominator here increase. I normalize it with the value and subtract it from 1. So let's say I measure 1 meter, but the true value is only 0.5. I will have 0.5 here. I divide it by 0.5, and the accuracy is actually 0. The precision is the ratio of the range and the statistical variance, and this is a concept we will treat only later in this course sequence. So I will not give you a definition for this just now, but you probably are best suited by remember this graphically. All right, so in summary, we can say that sensors never serve specific applications and do not solve any problem completely. What sensors do is measure a certain physical quantity in some approximated way. So if you truly want to know that quantity, you more often than not need more than one sensors. And if you want to use that quantity in some application, you probably will use a variety of different sensors that will help you to do that. There are very many sensors for the same phenomenon. So when you say I want to measure distance, you can do this in very many different ways, in using light, using sound, using the measuring the time of flight, measuring the phase shift, and so on. And so you have to be aware of that. All of these sensors have different trade-offs, and usually those trade-offs are somewhat qualified in their precision, accuracy, bandwidth, dynamic range, resolution, and other of these quantities that we have discussed. How to extract information from sensors is a different topic. We will talk about later in this class, and also how to fuse them is a complicated endeavor that we will talk about later in this course sequence. So this class is not just about sensing, but also about actuation, and I have a little video here which shows robot soccer, and I chose this example because it actually shows you the duality between locomotion and manipulation. So locomotion is moving. The locomotive, locos is the location, and motion is the motion. It's both from Latin. And manipulation comes from the word manus, is the hand. And you can now see how the robots here manipulate the ball and locomote using wheels and using legs. There are many, many different ways on how to do locomotion. There's rolling, there's walking, running, jumping, sliding, flying, you name it. In practice, we are mostly concerned with rolling. And the reason for this is because rolling is extremely energy efficient. So when you look at the speed that you can get versus the unit power that you have to put in, using a railway wheel is actually the most energy efficient. So I have very little energy that I need, and I can get very high speed. When I do walking, I need 10 times as much energy. So this is a logarithmic scale. And I cannot get over a certain speed. Once I do that, the mechanism is doing something that is called running. And running is fundamentally different because it's like galloping. You start losing touch with the ground. Running and walking are not very interesting, both in terms of speed and in terms of energy efficiency when compared with even a tire on soft ground. Now, as you go down and the ground becomes harder, this line moves down and approaches the railway wheel. And what is really not attractive to do is crawling and sliding like snakes do. So as a consequence, people have been terraforming the entire planet to be accessible with, or not everything, but most of the things we care about, including in your houses and industry, with wheels. And so this is why this is the dominant form of locomotion for now. When you look at different actuators to do that, we have different options, the most dominant being electric motors. And there's also a class of linear actuators, which you might want to use if you want to create walking mechanisms. And there we have more options. They are not only in electric form, but sometimes they use compressed air. It's called pneumatic or compressed fluids. Then they are known as hydraulic. And there are many, many, many specialty actuators like electro actuators and magnetic ones and inflatable, and a large number that we shouldn't cover here. So for the electric motors, the important categories are DC motors and stepper motors. And most importantly, there is the brushless DC motor, which has really revolutionized robotics. The motors are usually paired with a gearing system because they spin at very high speeds, and we actually want to rather slow rotations when we drive around or move a robotic arm, and an encoder system. Stepper motors don't need encoders. They allow you to count the steps, but they're usually bigger and less efficient than these brushless DC motors. So how does a motor work? In the most basic form, a motor is a coil that can rotate within a permanent magnetic field. And when you put electricity at this coil, you create a magnetic field, which will then be attracted and repulsed from this permanent magnet. So if I create a magnetic field by turning the power on, the coil will be repulsed from the North Pole here and attracted by the South Pole there, and actually flip around once. The magnetic field only comes when you change the current. That means when you turn it on or you turn it off. It doesn't create a magnetic field when you keep powering the coil. That means you have to switch the polarity of this electric field as the coil moves. Now you can do this with what is called a commutator, and this is a clever arrangement where you see I'm powering the left side of the coil with plus and the right side of the coil with minus because there's a gap here. And as the thing turns, this brush will hit, or this piece of the rotor will hit the brush here, and then the right side of the coil will be powered. Now, if I have AC current, I can power a motor like this directly, so with an AC alternating current. If I have DC current, like voltage that doesn't change, like out of a battery or something like this, I will need this commutator framework. And you see it here done using a brush, and it's a little more sophisticated. I'm using 3 coils to create a rotation here, but again, I provide the alternating current by using this commutator framework. Now, the commutator is subject to friction. You have to change the brushes eventually, so these motors are not very efficient. Since maybe 20 years, we have cheap and available brushless DC motors where the current switching is controlled by a little power electronics device which measures the speed of rotation of the rotor and automatically switches the current. Now, these things are much more efficient and have now enabled drones and also the breakthrough of electric cars, which now exists for more than 100 years, but never really became an interesting thing in the market. One reason for this being the motors not being efficient enough. A key motor innovation has been the direct drive. So you already know how the brushless DC motor works. I can change the polarity really quickly. In this case, I have a rotor where there are many magnets around the rotor, and I have coils in the stator. And what I do is I switch the polarity of these stator coils very quickly to essentially move this rotor ahead to the left or to the right as a function of the pattern that I apply. And this is very interesting because I have a hole in the middle where I can run wires through. So most robotic arms will use these kind of motors which have these holes in the middle. But I also get a very small geometry. And now I get high torque density. I get 1 Newton meters of torque for a small motor with just 10 centimeters outer diameter. But I have to feed it with quite some power. And in this case, the direct drive that you see here requires 400 watts, which is at 48 volts, around 8 amps. If you think about this, 48 volts is half of what comes out of the plug in the US, 110 volts. 400 watts is very serious power. It's a small heater, so these things get very hot. You also need to understand that the power electronics for dealing with these high currents and voltages is non-trivial, especially when you energize a coil. You will create a magnetic field. If you de-energize the coil, the magnetic field will collapse and it will create a very high spike of reverse voltage that will destroy everything that you connect to this motor unless you design it cleverly with a reverse diode that goes around the coil and the resistance of the load, which is known as a flyback diode. Now, this is just the detail. I just want to give you an appreciation of the electrical engineering that has went into the motor design and really now enables applications like robots that can walk and run in an efficient way, electric cars like the Tesla cars, or low-cost robotic arms. Another component you will need is the gear reduction, and here the key motor innovation in the last few decades has been the so-called harmonic drive. The harmonic drive is a very sophisticated mechanical device in which you can achieve very high gear reductions using very little space. And the way it works is the motor is mounted to an aluminum tube which can actually deform from this elliptic device that is rotating within. So really the motor is mounted to this green thing that spins inside something like a Coke can, and as it does that, it deforms the outer diameter of that aluminum can, and it hits the gears, the teeth of an outer ring. And whenever it does that, it moves the outer ring slightly forward. And so in this case, this green thing has to rotate 50 times for this outer ring to rotate once. It's difficult to understand until you see it. You can check out the internet YouTube videos, how these things are made. People actually 3D print them. So then you can really understand if you're interested. They have a lot of advantages. They're very efficient and not backdrivable, which means when I turn the outer side, I cannot turn the motor. Now, modern robot joints are packages out of these that are made from these different components. You would have the direct drive motor, you have the harmonic drive gear set, you have an encoder that is shown here. You would have a brake that would allow this thing to be stopped when power is shut off. And what did we not cover? Possibly a joint torque sensor, which measures the deformation of this blue piece here using strain gauge sensors. I include a couple of links for you to watch how these things work on YouTube if you're interested. But again, this is just a little intro so you know what's going on. Now, finally, there's an interesting class of actuating sensing systems, which is known as the series elastic actuator. In this case, you do not connect anything directly to your motor and gearbox, but you connect your actuators to a spring, and the motor has to move the spring so that what you connect to the system also moves. This is very interesting because when I hit this, I don't hit the motor, I don't break the motor, I don't break the gearbox, but I have some damping because I do hit the spring. So the idea here is that these devices can also be safer when working with humans because I have a little leeway. I have to first compress the spring before I get the full force of the motor. But more interestingly, I can again use Hooke's law to measure the displacement and from there enforce the force that the robot is actually exerting onto the environment. Now, this technology didn't work out very well. Nowadays, it is done this way with these joint torque sensors. In this commercial robot designed by Rodney Brooks, Rethink Robotics is now dysfunctional. And when it didn't work, they started another line where they sold only single robotic arms. And I still want to show you this because it has really been a great innovation in terms of human-robot interaction. The robot arm has a display that communicates with the workers, and they've been pioneering a lot of applications, pushing people to set those up by themselves. In practice, this isn't really the case. People have to build fixtures and things like that to easily interface with the robot. The programming was rather simple with a graphical interface using behavior trees, which we also learn in this class. But at the end of the day, the robot hasn't been successful. So this is an application where the force or the spring makes a lot of sense because it adds compliance. The system is not stiff anymore, but the spring will give in a little bit as you do tight insertions. Now, this is an interesting task. When you place 50 of these PCBs, the robot will be able to put them all into this machine, one after the other. So we could see how this might save some labor. It can then also take the devices out again at the end. Another innovation that the Sawyer had is it had a wrist-mounted camera. So in this black thing here is a camera, so it can actually see and find these devices on the conveyor, so you don't have to buy an extra camera. So this is also an interesting application. The robot is actually interfaced with the computer by pressing the mouse button. which is a very simple way of doing things. And this is not very much done in practice, but it is actually interesting in terms of user innovation, possibly really empowering people to program such complex systems. Well, with that, we're coming to the end. Computer science, and this is a computer science curriculum class, has for long left the challenges of the analog world behind. When computing started, people were using valves and vacuum tubes to build computers, and they really had to understand how the physics of these valves worked. Sometimes you would have what was known as a bug, which is a physical bug making his nest or something in between the legs of one of those valves, and then the computer program would crash, and then people would have to go in and debug the computer. Nowadays we have transistors. You can put 1 billion of these on a very small square inch footprint, and we really don't want to know anymore what's going on in the computer, except maybe for temperature or speed. With robotics, this is the opposite. All of the sensors and actuators are noisy and have fundamental limitations that, if you don't understand, will make programming the robot very, very difficult. I hope this class gave you some initial idea on how these sensors work and what the problems might be. You will get more practice only once you start using them in the labs. And I think it's really dealing with this abstraction, jumping from the physical, noisy world to the discrete world of the computer, that makes robotics difficult.